So if you go through the program of EBMT 2022, you will see the nursing program is the largest. And they had 23 sessions compared to other. And so the indication of transplantation in recent years has expanded. And that's led to not only in the number, but also in the type of transplant, or I would say cellular therapy. So the CAR-T, as you saw yesterday, there was a complete whole session about CAR-T, and CAR-T has nothing to do with the stem cell transplantation. And it's another type of cell that we get from the patient, we manipulate genetically, and we expand it ex vivo, and we return it to the patient. So it's very important to understand how these cells are made. It's an introduction to the nursing group. And honestly, when I attended last year, this year I was going to attend, but then the war in Ukraine, really, they canceled the physical meeting and they made it only virtual. So I usually go to the nursing meeting because they are first very educational. You see the A to Z understanding. Unlike the physician, they present the study, middle of the study, and there is graph up, graph down, progression-free survival, overall survival, things that doesn't explain the basic science of how things are being done. I spoke yesterday to the president of EBMT. I was honored to see her, Prof. Anna, and I told her when the EBMT will change their names. The American already changed their name from SSBMT to American Society of Transplantation and Cellular Therapy. It's a very important component. And she told me that there is a board meeting and she will discuss this issue. Then I saw Dr. Al-Askar. I told him, when you are going to change the society name SSBMT, it's old-fashioned. He said, after EBMT, if they change, we will change. If they will not change, we will not change. Because it's a heritage, it's like something from the past. But in my hospital, the name of the department changed from hematology and HSCT to hematology and TCT, transplantation and cellular therapy. It's very important. Maybe in King Faisal, they have the CAR-T, and they really should match, but all transplant centers should match the trend toward the move to meet the new areas of transplantation. So talk this. So my presentation is basically going to the basic of how to do the CAR-T. My master was cellular therapy before. It was in the last century. This was about 23 years or 24 years, where my thesis was on getting T-cell, isolating gamma delta, expanding ex vivo gamma delta, and return it back to the patient. So it is like CAR-T, they take T-cell, except I wasn't doing genetic modification because the gamma delta, they have the capability, they don't need education. They are very well-educated cells. So that was the purpose, but then the molecular targeted therapy came and I didn't complete the cellular therapy. Anyhow, 20 years later, it's there. So to our nurses, be ready. You are our partners of success. And as it was said by Ed Thomas, the father of transplantation, nurses are the success of any transplantation. I will say nurses are the secret of success because everyone is claiming that they are the success. Yes, it's a teamwork, of course, but if you want to know the secret, because, we physicians put the order, and then who will take care of the patient? Who will recognize the cytokine release syndrome or the ICANN or all toxicities of cellular therapy or transplantation? Nurses. They are 24 hours with the patient. Physician, we can calculate how many minutes or sometimes hours if the patient's sick, but it's very few. So we really need to have strong nursing, education, collaboration, and putting the basics together. Gene editing is the method. So I was talking in Harvard, they had the course. It's called CRISPR-Cas gene editing. And that's the basic of how they are doing the CAR-T, so chimeric antigen receptor. So it's important to know from where this came, what's CAR-T, and that's what I did in my hospital. I did a grand round about CRISPR-Cas, and then I talked about gene editing, and then I talked about the CAR-T. I have no conflict of interest here. So what's the CRISPR? The CRISPR is a method that the prokaryotic, the bacteria, will enable itself to fight the virus, the bacteriophage. So, you know, the bacteriophage will attack the bacteria and use its DNA to multiply. So I'll go to the picture here. So this is how the bacteriophage attack the bacteria, inject its DNA. DNA is replicating, and now they end up with the bacteria dying, and the bacteriophage is multiplying. The bacteria, they have the mechanism of CRISPR-Cas9. What's CRISPR-Cas? So it's clustered, regulatory, interspaced repeats of using endonuclease to cut the DNA of the virus and prevent viral replication. So it's a gene editing. You cannot see what happened in the down, that the virus, the bacteriophage enter into the bacteria. Bacteria already, they have the CRISPR-Cas, they're cutting the DNA, put it aside. The bacteria survive. And the beauty of this gene editing, that it's inherited. I mean, it's transformed from one generation of bacteria to the next generation of bacteria. Unlike we give chemotherapy, it's one dose. You have to give repeated doses. But CAR-T, you give the cells. These cells can multiply and replicate, and they can stay in the system 3 months, 6 months. So whenever there is chance for the disease to come back, they are there. So they are very efficient in eradicating the disease. So that's how we learned this lesson from bacteria. We took it into human. And by the way, gene editing has been in practice for years. It was this century, second decade, that they had the introduction of clinical, medical use of CRISPR-Cas or gene editing. But it was before in this, the farming, the agriculture, the animal breeding, they use gene editing. So they have the rice, there is gene editing, so these rice crops will have resistance to any parasites or infestation. So they have large amount of production. And in industry, in many things, it has been in our life. Lately, it came into medical. And you can see the benefit of having this gene editing. So now we will talk about the embryonic. Embryonic, of course, we are not allowed to do any research. So the scientists, they discovered the induced pluripotent stem cell, and that's how so you can take embryonic from the blastocyst, or you can have induced pluripotent stem cell, and you can get whatever cells you want. And then you can do gene editing with these cells, with whatever, and reintroduce to the patient. So here, beta thalassemia is a very excellent example of successful gene editing using the CRISPR-Cas. Yesterday they talked about sickle cell. I didn't attend, but it wasn't successful as beta thalassemia. Beta thalassemia now is an approved indication of therapy in patients with beta thalassemia measure as a cure. Transplant is one area, but the gene editing is another area. And that's what they do. They have the patient with the genetic disorder. They take the cells and they convert it into induced pluripotent stem cells. They have the genetic defect. They repair it with the CRISPR-Cas gene editing, and then they differentiate and then return to the patient. Beautiful. Beautiful method. It's peaceful. Of course, gene therapy, there is conditioning still. So we cannot live without nursing. So no dream. It's not as simple because there will be admission. Patients should be fit for receiving conditioning in order to be able to accept these newly modified, their own cells. So that's the genetic editing and where it will lead us in treatment of diseases. CAR-T is a new therapy. We have to be careful with anything new. We really need to monitor. So among the challenges is off-target effect, meaning you do gene editing, but you don't know what's the function of this gene. So what are the consequences? That's one part. Another part, making sure that it is giving the target that you are aiming to. Another risk is the P53. So Allah subhanahu wa ta'ala created in our body a very efficient mechanism. Anytime you have the cells, the gene manipulated, there is a gene called P53. It will be activated and this cell will die. So in order to overcome this P53 mutation effect, they induce offsetting or silencing of this P53. So CAR-T, they are dividing, they are giving the target that we wanted, but without P53 on board. And when you lose P53, which is a secure mechanism against any mutation happening, so we should monitor all patients receiving CAR-T, even if it is their own cells. We really need to be careful. It's very effective, as we saw yesterday, but it has to be done with long-term monitoring, making sure that we are not getting some of the unwanted effects. So that's the P53. Germline, in human, we shouldn't touch. That's a principal ethics now. Gene editing is there, but germline, we should not. So what happened in China, there was a scientist there was a person who had HIV, and he wanted to have offspring without HIV, which is possible. I mean, there is the AZT they can use during pregnancy, etc. But he wants his offspring, the IVF product, to be resistant to HIV. And we know that CCR4 is a receptor that, if present, these cells will be resistant to HIV. So he went to the scientist, he introduced this CCR4 into the fertilized ova. So now we are manipulating the germ line. And he was successful to get offspring, 2 daughters, IVF. They are resistant to HIV, but the ethical issues came after. And I was attending ASH 2018 annual meeting, and this had a hot discussion. How come we allowed this to happen, germline? And what I heard lately, that he was captured and he is in prison and he will be for decapitation. Very strong punishment. I don't think it should be this way, but there should be ethics to handle. So germline we should not touch in a human. And then what they are after in the future, that we can now get like gene editing from allo. Like you don't need to have the patient. Sometimes we have problem of getting the CAR-T from the patient. So now what they are after, universal CAR-T. Because if you gene edit HLA typing or presentation on the cell, so you can have a cell without HLA typing or antigens, and with the gene editing effect, you can return it to the patient with what you want to get the effect. So there are lots of changes. Of course, the use of CRISPR in diagnostic tool is well established, and the therapeutic use of T cells, that's the usual T cells from tumor-infiltrating lymphocytes. This was last century. They take the T cells from the tumor, so they have the tumor with T cells, they extract T cells, and then they expand it, return it. There's no gene editing. That's what's happening with CAR-T, the same. There's tumor, there's T cell, they take the T cell, they edit it to be effective only for the tumor-targeted cell and return it to the patient. So that's the method change. And by the way, CAR-T is not only for malignancy. So anytime you have something you don't like, so if it is physical, you can ride your car and hit the person. Or if there is a disease, you can create a CAR-T, chimeric antigen receptor, against, let's say, a patient with hemophilia inhibitor. The cells producing the inhibitor is B cell. So you can develop a CAR-T against the specification of the B cell and get rid of the inhibitor instead of using these bypassing agents and all these dilemma we are getting with it. So all diseases, not only hematological malignancy, aging, multiple sclerosis, all neurological, different disease. Define what target you want, develop a specific CAR-T, and hit back. So that's what's happening. So universal CAR-T using multiplex CRISPR-Cas9, and then you can use also the animal as a tool. So let's say this patient had, she needs a pancreas, you can take induced pluripotent and you can put it in the blastocyst of this chimeric blastocyst and return to the pig. Pig will have the pancreas with human cells, and then you can take the pancreas transplant because it's from the same patient. So there are many advances in this cellular therapy. So nurses should be aware, and their knowledge, basic science knowledge, better than physician. And that's other application is reconstructive, regenerating the hearing ability. You can imagine anything missing, you can reintroduce it through gene editing method. And that's my last slide, and thank you very much.